So we will start with a colloquium this afternoon, and this evening we have with us Professor Arturo Menchaca, who is a professor at UNAM in Mexico City. He did his undergrad studies in physics at UNAM, and then he did his PhD at Oxford. And after the PhD, he did some postdoctoral position at Berkeley National Lab. And then since then he was a professor in different places in France, in Chile, and he took positions in Argentina and in Mexico. And he works in the area of low energy nuclear physics, and he's the founder of the nuclear physics division of the Mexican Physical Society, and he's also was the former director of the Institute of Physics in Mexico. Also the former president of the Mexican Academy of Science, and he has been awarded many prizes in the field of nuclear physics and also in development of science. And at the moment he's a member of the Advisory Council for Science for the Mexican president, and he works in the area of now also in high energy nuclear physics in the ALICE experiment, and the AMX experiment is using nuclear physics to study various things like pyramids and volcanoes. And so today he will talk about his work, so let's welcome him to Kansas City.
Do you hear me? Is this working?
Yeah.
Okay. Well, I've been told this is the pointer. So, well, thank you for being here, and I will describe to you an experiment that we did, an experiment we are setting up to do using muons to investigate the inside of large volumes like pyramids or volcanoes. Okay, so let me see. I have to. There. Okay. Now I've been told this is a colloquium, so I apologize for my high energy physicists and nuclear physicist friends. I will describe to you the motivations both in archaeology and volcanology, because this is applied science. There's no new physics. If half of you can go to sleep and I wake you up when the thing comes. Okay, so there will be, I will say some physics, and then I'll describe my methods and talk about the instruments and show you some of the first results in both type of experiments. Now this is very simple. Just to give you an idea, I will tell you more about what the muons are, but I suppose you have a uniform flow of penetrating particles that go through a volume. Okay, this is a large volume that has an empty space someplace. Okay, and suppose your radiation is absorbed by this volume. Okay. Then what you would expect to see on the other side is that your flow will be attenuated everywhere, but will be less attenuated in the part where this empty space is. So that is the whole idea. Okay, so I could stop here and you would have already understood what I do. Okay, so I will describe two places where we have used this technique. Okay, one of them is applied to archaeology. Okay, and archaeology, I will describe a little bit of the motivation. I am not an archaeologist; I am a physicist. So, if there is an archaeology here, please don't be too harsh on me. Teotihuacan is the place that we are going to be working. Teotihuacan is the largest archaeological site near Mexico City. It's about, well, some 25 kilometers away from Mexico City. And Teotihuacan, oh, thank you. Teotihuacan was built like 2,000 years ago. And Teotihuacan was a very large, had a very large population, like 150,000 people. Now that doesn't sound like too much. But 2,000 years ago, there were very few cities in the world that had 150,000 people. So this these people were, let's say, this city was a large city for all standards, and of course, was possibly the largest city in America at the time. Okay, I hope New York. There are no New Yorkers here that will you're here to contest this concept. Okay, now Teotihuacan has pyramids, lots of little pyramids, but it has two big monuments. The Pyramid of the Sun is the subject of of this application. Okay. Now I like to show this picture because this is actually a drawing by an artist drawn in 1878. Okay, because this monument was then in about 100 years ago. It was taken over by archaeologists who covered it and pretty much did. They rebuilt it. No? Now it looks like this. Okay. So this is our monument, and the monument. The Teotihuacano people were very civilized, but they didn't have a written language, and that is very sad because we know very little about the purpose of their pyramid and many other things. They only had drawings and things. They were very good at that, but not written language. We don't even know what the Teotihuacanos called themselves, because Teotihuacan is a Nahuatl word, and the Nahuatl arrived in that part of Mexico like 600 years after the Teotihuacano culture had disappeared, or went extinct. So this is the limited information. And one of the questions the archaeologists ask themselves is, why did they build these big monuments? No? Now, building, what do I mean a big? 2,000 years ago, these people put together 1 million cubic meters of soil, okay? And what on earth would drive them to do such a thing? And there are two theories. One of them is that they built this thing just as a commemorative monument, okay? So they would celebrate some things. Or it could be a tomb, okay? It could have inside the remains of somebody very powerful. Indeed, you need to be very powerful to have 150,000 people working for you to build such a monument, okay? So these two are competing concepts. This is one thing, and I will elaborate more onto that, but I will take along the way the two fields, okay? So the other application is to volcanology, okay? Mexico has pyramids. There are about more than 3,000 documented pyramids in Mexico. Many of them are not even kept because Mexico doesn't have enough money to keep all these sites. But we also have lots of volcanoes, okay? And volcanoes, there are about 22 volcanoes that are considered active, okay? But there are different definitions for that. And there are about 12 which are really active in the sense that they are emitting some fumes, okay? And there are 2 that are so active that they are a menace to the population. So this other field of application for our expertise is related to assessing on the risk that these volcanoes represent for a large population. The Popocatepetl volcano is about 40 kilometers away from either the Mexico City that has more than 20 million people or the city of Puebla that has more than 3 million people. So these are the two subjects to which I'm going to apply, or I'm going to describe our application. Now, let me tell you a little bit about the history of muon attenuation. The first person to have ever used muon attenuation for something practical was a Mr. George, who was someone in Australia who wanted to measure the thickness of the snow level, the snow that fell onto the Australian mountains, skiing mountains. As you know, the skiing could get dangerous when they have too much snow. And so this person, Mr. George, what did, he took a detector in the summer and put it in this mountain, and then he will measure in the winter the attenuation of his count, okay? And by comparing, he would know how much snow he had. So that's the first published application. Then in 1970, around this date, Luis Alvarez, this fellow here, he faced an archaeological problem. He was the first one to apply it to archaeology. Archaeological problem is related to the fact that this pyramid here, as you know, near El Cairo in Giza, there are three famous pyramids: Cheops, Kefren, and Miserinos. Okay, and Cheops was the father of Kefren, and Kefren was the father of Miserinos. There are these three pyramids, and Cheops has a very rich internal structure of tunnels and chambers and things, but Kefren has only one known chamber at the base near the axis of symmetry of the pyramid. And archaeologists believed that the architects of Kefren were more clever than the architects of Cheops, so that Kefren was still there, okay, but his remains were not found because they were well hidden inside this monument. So Luis Alvarez proposed a technique to investigate the volume. Okay, one way to do it would have been to take apart the pyramid and see, but nobody would allow that. So the other thing is to use a non-destructive method to look through the pyramid. And this is what Luis Alvarez used, same idea. He had muons, no? And these muons would somehow, he used this chamber at the bottom of the pyramid, and he will install there a muon tracker, okay? And by looking at the count rate, mapping this count rate as a function of the direction, he would try and find empty spaces, just as I described in the previous transparency. Muon attenuation has also been used to map caves in mining and other applications. And recently, there is a Japanese group that have used it in volcanology. Okay, you know, the Mexicans and Japanese people share the burden of having their country full with volcanoes. They are a menace also for the Japanese. And this fellow here, who's a very clever person, he decided to use this muon tracking to try and learn something about the internal structure of a volcano. I will elaborate more on that. And well, here in Los Alamos, there's been a development to use the muon tracking to try and find or try to detect heavy metals, high atomic number particles, by measuring doing measurements on trucks and containers going through the Mexican border into the United States that were labeled as having oranges, let's say, you know, but that had inside highly dispersing materials like lead, okay? And many of you will understand that if you have lead instead of oranges, chances are this lead have some sensitive material that you don't want to come across the border. So these are many applications. And you might have read recently this very same person used the technique to map the reactors in Fukushima, okay, to try and find the structure, the state of the status of the Fukushima reactors. Okay, now this is a colloquium, so I will tell you what are muons, okay? this is the standard model. Particles are made out of these 12 particles, okay? These 6 live inside nuclei, and these 6 live outside nuclei, okay? And the best known fellow is this here called the electron, okay? Which is the one that allows you to see me and to hear me, okay? And this is the only stable particle, or charged particle in this side of the table, okay? And the electron has a heavy cousin that is 200 times heavier than the electron, but it's unstable, okay? It's unstable. And he has an even heavier fellow here, and even more unstable, okay? But the one that we are worried about is muon. And the only characteristic you really have to keep in mind is that this fellow is heavy, is short-lived, but has the same charge as the electron. What does that make any difference? Well, the cosmic flow has electrons. There are cosmic electrons. But electrons, as they interact with matter, they deviate because their mass is very small. They have the same charge, but they collide with electrons in the atmosphere, and in every collision they get large deviations. So they are not good for tracking. But if you use muons, muons are very heavy. When they interact with electrons, they lose energy. I'll elaborate more into that. When they go through matter, they have a lot of mass, so they travel pretty much in straight lines. And that's good for tracking. So that's all you want to know. I am not going to discuss the Higgs particle or anything like that. That's all you need to know. Now, I've been talking about cosmic rays. This is a 101 lecture of cosmic rays, okay? You know, in the sky, you have all these reactors that we call stars, okay? And these stars have a lifetime. And some of these stars, at the end of their lifetime, explode, okay? They exhaust their fuel, and they explode. And when they explode, they throw away the matter of which they are built, and this matter is mostly hydrogen, okay? So you have a lot of hydrogen being thrown out into space. Now we are talking about hadronized hydrogen. These are charged particles, and as they come, I mean, some of these particles travel through space, and space is full of magnets. The Earth is a magnet, the Moon is a magnet, the solar system is a magnet, our whole galaxy is a magnet, and when you have these particles traveling through magnetic fields, they deviate. So they are affected by this magnetic field, so they follow sort of like a pinball trajectories. So by the time, if you have our whole galaxy having every once in a while a supernova explosion, okay? These supernova particles, these particles, very energetic particles, are traveling and are trapped in our galaxy, and somehow they become. If you are on Earth, try to figure out where these particles come from. That would be very difficult, because somehow these particles, especially the lowest energy ones, they travel in very random trajectories. And that is good for us, because this means that you have a pretty uniform flow of these particles, and this would somehow, you are not going to have located sources, but you're going to have a uniform flow. And that is important for imaging. Now, out of the primary cosmic rays that generate these muons, okay, we know lots of things. They have to be measured. These are mostly protons, and they have been measured over an enormous range of energies, and you see this thing is a pretty logarithmic that runs over 32 times 10 scale. Orders of magnitude. So it is really, all I want to tell you is that we know a lot of these things. Most of the bulk of these things we understand very well. There's no new physics as far as I am concerned for that. Now, these energetic particles have to get close to the Earth. And the Earth is a magnet, especially in the tropical countries like where I come from, okay? So these particles as they come to the Earth in our neighborhood, are going to be crossing the magnetic lines of the Earth perpendicularly. And so they are going to be deviated. So these particles need to have a lot of energy before they can actually penetrate and interact with the atmospheric, the atmosphere, of the Earth's atmosphere. So we are talking about pretty high energy primary particles. And as I said, these particles are mostly protons. Protons are the nuclei of hydrogen. Now, when they do, what happens is that you produce a shower. This means your proton will come and will produce some hadrons, very short-lived hadrons, and these hadrons will eventually decay into muons, to the point that if you measure the flow of these particles as a function of the atmospheric depth measure, this is the seaside, sea level. Mexico City is around here, okay? And I guess you must be living around here, okay? So somehow you see that the charged particles, these are neutrinos. We are not going to care about neutrinos, but the muons are by far the most abundant charged particles coming to at the Earth's surface. Okay, so this is the type of particles that this is the type of flows that you are going to be detecting. Those of you who worry about this thing, this is what I described. You have a proton, it hits a nucleus. This nucleus produces, in the process you produce, of course this is not balanced and you can laugh about it, but somehow you have produced pions. Pions decay into muons and neutrinos, and you have pions have very short life. The half-life is about 26 nanoseconds, whereas muons have of the order of 2 microseconds. So there is about 100 times difference in the two. Okay. Now you say this is too short, but these particles are very high energy particles. They are relativistic. Their life is extended, and they have enough time to cross the atmosphere. Okay. Now the atmosphere is not too thick. No, this thing is happening at about 100 kilometers, and a relativistic particle travels 100 kilometers in no time. So they survive. Okay. Now, for the muons themselves, we know they have been measured everywhere. Okay, and we know very much their spectra, and we know the spectra as a function of the polar angle. So you can, this is no, we understand it, and there is no problem. The penetration of this radiation has also been measured with some detail, and you can see this is the depth in water, in kilometers of water equivalent matter. Okay, and you can see that at 10 kilometers in the sea, you can still detect muons. Okay, but the muons get attenuated. Okay, they get attenuated as they go along. This is 1 kilometer and 10 kilometers. Now for my pyramid, I'm going to be working in that part. Okay, for the volcano, I will be working on this end. Okay, but it's still, I have muons. I'm going to have enough muons. And this means is that if I am going to do this experiment in a pyramid that is tens of meters tall, I can do this experiment in less time. Or I need, in this part, I'm going to need a much bigger detector in order to make sense or to be able to count. This is all what it means. Okay. Now, this is the most complicated plot, but I'm sure there are experts here who would like to know more about it. So, this is the rate at which particles lose energy depending on their energy. Okay? These particles, the process of attenuation is that you have, as I showed, a whole spectrum of particles. You have low energy particles, high energy particles, okay? And these so you have to understand how they lose energy as they penetrate matter. Yeah? Most of them, if you ignore the very low energy ones, most of them are going to be losing energy through collisions with electrons of the media, and this is going to be, they are going to cause ionization, okay? So most of these things, most of my particles, if you have some imagination, are going to lose energy at about the same rate, okay? Some of the very low energy ones lose energy much faster, but most of them are going to be what we call minimum ionizing particles. So basically the count rate is going to be, will give you a lot of information. If they have a lot of energy, then what happens is that this thing explodes. They lose energy at a much faster rate, and this is going to affect, this is going to limit what I can do in the volcano part, okay? Because I need many energetic particles to go through the volcano. But for a pyramid, I'm going to be talking about, I'm just counting, okay? And this is all what I need to know. One factor that is important is that so far I've been lying to you because I tell you these particles travel in a straight line, and that is not so true, because these particles are interacting with electrons. And even though they have 200 times their mass, okay, they are still going to be kicked away from the trajectory on every collision, a little bit. So there is this French guy called Molière, it has nothing to do with the writer, and this person measured, he went into, well, he had a theory for this multiple dispersion thing. It's a small thing. In the pyramid, this is less than half of a degree, okay, this dispersion. Now, half of a degree sounds like little, but it blurs my image, okay? And this is going to be more of a problem in the pyramid, okay? The pyramid, my spatial resolution will be related to this parameter, okay? And multiple dispersion is affected. It goes as the inverse of the energy of the particle, okay? If my particle has a lot of energy, it will be less deviated than if it has less energy. And it also, of course, is related to how much matter I traverse. If my muon traverses a lot of matter, then it gets more deviated than if it traverses less. The equation is very simple. Oops. Now the detection technique, in this technique, contrary to what happens in radiology, in imaging with radiology, you have a point source, okay, and a photographic plate. In this case, as I described, you have a diffuse illumination. Your particles come from all over. So in order to reconstruct an image, the same as happens with your eye, you have to reconstruct the direction of every muon in order to have an image, okay? So the detection technique is very simple. You need elements in your detector that identify the muon and discriminate it against radiation. There's natural radiation. There are lots of gamma rays in a cave or things like that. So a particle that goes through the whole detection system and produces a coincidence between the two extremes of your detection system is a muon. Only a muon can go through, okay? And once you know that a muon is, then you produce a signal that is a trigger to your thing. And so you locate in the middle detectors that are position sensitive, okay? So you measure, say, 3 positions along the track, and with 3 points, you can reconstruct the trajectory. And so these things, you digitize, store them someplace in the disk, and then you process that offline in order to reconstruct your trajectories. So that's the technique, okay? Now, this is all you need to know about the technique, okay? So the archaeological application, I will go back to the pyramid and tell you a little more about it. The pyramid was studied by archaeologists about 80 years ago. The first excavation was done. It's a tunnel that runs from the back to the middle of the pyramid, and then 15 years later, they continue the tunnel up to the end, okay? They actually did it this way, and you know, archaeologists are not good architects, and they really quite meet in the center, but that's besides the point. What is important is that what they found inside of the pyramid is that the pyramid is just made out of soil. It doesn't have an internal structure, okay? other pyramids have. In Mexico, there are lots of pyramids that are superposition, like Russian dollies. They are superposition of pyramids. Okay, every 52 years, I believe, the ideology of some of these, the local population was that they had to rebuild, so they built one on top of each other. But this pyramid in particular, it's only soil and has no internal structure. So this was deceiving for them, because having investigated less than 1% of the volume of the pyramid, they already knew, and they couldn't have, they just didn't allow them to have more digging, because which direction they were going to dig if there was no sign of any internal structure. Still, in 1962, a lady an American lady who was powerful enough got permit to dig on the top with a different argument. And she didn't find what she thought she was going to find, but still she found that the pyramid is soil on top too. So there has been not more digging inside. On the outside, on the periphery, there has been some digging, but the main volume has not been investigated. So what does that mean? There is one other important secret, is that in the 1970s, an American tourist, again a lady, went there with a dog, and the dog fell in a hole. And she started screaming for her dog, okay? So they had to go and look for the dog. So they paid someone, and the dog actually made one of the most important discoveries in the site, because this dog turned out that he found that there is a tunnel running under the pyramid, okay, 8 meters under the pyramid, and this tunnel is a natural tunnel. It's a man-made tunnel that has the following shape. The entrance is here, and it looks like a worm, okay, except that it has this structure, okay, this has at the end. But when you look at this, with very generous eyes, you will see that this could be considered as a straight line. And when you see this thing superimposed with the pyramid, then you see that this thing is centered on the pyramid, okay? And it goes near the axis of symmetry of the pyramid. So people immediately realize that probably this tunnel, which is previous to the pyramid, okay, was the very reason for which the pyramid was built, okay? So these things are related, and there was a very interesting discovery, okay? But this is all, they say, well, so this is very clever. But there was nothing much else to do. The tunnel itself had signs that it had been blocked, but when the dog was lost and recovered, they had already been violated. Okay, so these seals, there are signs that they were there, but there have been some sacking, and somebody just took off or whatever there was in the tunnel. Still, you see, you have a pyramid, you have a tunnel, and you have a cave, you have a place where to put a detector and repeat the Luis Alvarez experiment on this, which is a very similar archaeological motivation, okay? So this is the relationship. If you are asking what is the relationship between Kefren and this thing, is that you have two pyramids that you want to investigate the volume, etc., etc. Okay, so this is where we put our detector. I will show you just some photographs, also to show the difficulty. These Muon trackers tend to be big detectors, and they have to go through that door, which is only like about 80 centimeters wide and 1 meter and 20 on height. So this photograph is quite old. It's like year 2002, and we took a simple Muon detector system, and we measure outside. And here we measure the first muons ever measured in this pyramid. So the thing had to be. Now, one thing I didn't tell you is that these experiments, because it's unlike radiography, doctors, MDs, know what they expect to find inside of a body, because they have in their training they have gone through the remains of many people, so they know where to find the heart and where to find what is inside. In this experiment, you are doing this experiment on a body that you don't know what's inside. That's the point, no? So what we rely for this thing is that we know the external shape of the pyramid, and the physics is not new, so we can simulate, okay? So we use one of these simulators generated at CERN for this thing, GEAN something, and you transport your radiation through the pyramid, assuming that the pyramid has an empty space inside, okay? So you just use the pyramid as a target. But you need to know the external aspect of your pyramid, because your target has a topology, okay? So we had to do a leveling, and this leveling we had to digitize 250,000 points. That one, someone who knows what I'm talking about giant, would immediately recognize that having a target for a nuclear physics experiment is very different than having a 65-meter high target. Okay, it's just a complicated thing. It can be done, but this is it. I'm not going to go into many details, but it's just to please those who are experts. We build our detector using multi-wire chambers, and this experiment is complicated in the sense that you cannot do very sophisticated technology in a cave that is 100 meters long down the earth, okay? It's humid, it's miserable, it didn't even have electricity. So it's a lab that is very difficult to work inside. So your technology, you cannot drive in a lot of power. So our experiment could not be very sophisticated. I mean, I know my colleagues here would have liked to have, to read every wire in there, well, that cannot be done because you have to drive so much power into this tunnel. So we use multi-wire chambers read by delay lines and things like that. And the most sophisticated thing is that we digitized we digitize every signal, like a scope on a flash, using a flash ADCs, 12 flash ADCs. So this is a detector in our lab. We are talking about the year 2010. Now, let me tell you one thing, that doing things in Mexico take a long time because you have to get the funding, you have to get the permit from the archaeologists to use the site, and you need a lot of influence. It's not that simple, okay? Well, Luis Alvarez was very powerful. No? I mean, he just proposed this thing, and he was but we were not that powerful. But still, we got enough power to have money to build a detector, to have the influence to get the permit and so on. So we built a detector. The detector was fully built by us, which is, I've already described to someone why we wanted to do it ourselves. There were American colleagues who wanted to give us the detector, but we didn't. We decided to do it ourselves. Now the detector, there was no electricity in about 1 kilometer away, so we had to ourselves put a pipe with the cables, okay? And then this is a Sears Roebuck garden shack, okay? That we put inside. And these are our colleagues. They are driving through the tunnel. The tunnel has been there for 2,000 years or more, okay? But people say, I mean, you see there is no support for the tunnel. It's not a tunnel that has this is just like that because it's an archaeological site, okay? And we worried about it, but it turns out that Mexico is a very seismic country, but this tunnel is probably the most secure place in Mexico because it has been there for 2,000 years and the tunnel is still there. So although we got nervous about it, you can go through there. And so that's the detector already installed. I'm not going to give many details, but some of you, I mean, may even, because I showed the Luis Alvarez detector, it looks just about the same, except that Luis Alvarez used an older technique, because multi-wire chambers were developed by a former student of his years later, okay, who got a Nobel Prize, by the way. So, this is what we did. The detector was placed in here, and we made 2 measurements over 2 years. 60% of our data are with the detectors just looking straight up, and then 40% of the detector we tilted to see a little more of the volume, okay? So this is the data that we have taken. Now, when you do an imaging system, you should be able to reconstruct the known features of the pyramid. And the known features of the pyramid, this is, our pyramid is, unlike the Egyptian pyramids, this is like a wedding cake. It has different levels, okay? So we should be able to reconstruct these different levels, okay? And this is indeed what we did. In here I show our data, which is the solid line, and the data is presented against the thickness of measure from our detector to the surface of the pyramid. And you see that these two don't match at all, okay? So when you have more thickness, you detect less muons. When you have more muons, it's because there is less matter, and that's exactly what you expect, okay? So, and you do, these are 2 cuts in our data, and you see in 2 different cuts, you see the same anti-correlated structure. So, and this thing, I'm not going to go into detail, but they coincide to where you expect these structures to be. Now, this is our very preliminary picture of the pyramid, superimposed on the pyramid on a level above the pyramid, okay? And what you see is very difficult to interpret, and this is why we are a little bit stuck. But what you do see globally is that this color, the brownish color is low. This is measuring density, okay? So this is less density than this part, okay? And our hypothesis, the first thing we thought is that this is, you see that's the north, this is the south. For people living in the northern hemisphere, the sun shines on the south most of the time, okay? So this pyramid is less dense on where the sun shines. So probably our pyramid is somehow drying out, because 100 years ago the pyramid was recovered. It was covered with stones, okay, to recover its original shape. But they used cement, that is the standard cement that was sold 100 years ago, okay? And this cement it does not allow water to go in very efficiently, okay? So in the sun, your chances are that you are more efficient. I mean, it's inefficient for water to recover, okay? So in Mexico is a tropical country, so it's pretty much warm all the time, and but it only rains on a certain season. So this thing is less effective. So our hypothesis is that the pyramid of the sun, we don't know. I'm not going to discuss whether if there is a thumb, but I can tell you there is a general feature in the pyramid. I gave a talk like 2 years ago. I thought it was in the public like this, but it turned out to be someone from the press when I gave my talk. And this is what happened, okay? I don't know if you read Korean, okay? But this is, okay, the same thing. You see the Smithsonian Museum, Mexico's pyramid of the sun is slowly turning into a pile of dust. And you go on like that, no? So, new scientists, whatever. This, archaeology, of course. This, and if you go and type in Google, Menchaca pyramid, okay, you are going to find thousands of in many languages. There is, and this is pretentious, but I cannot avoid saying this is probably the most, the better known publicly experiment going on in Mexico, scientific experiment, okay? So just because this is, I mean, if I were to say something about what the experiments we do at CERN, I'm sure we will not even get a note someplace in the end of a journal, okay? Now I'll go to volcanology. This is almost the end of my talk. And in volcanology, the problem is size. The difference is size, okay? Because these things are, I don't know, they are much bigger beasts, and you need to worry about them. Now, I will try to convince you about the volcanological problem that we want to try to solve, and then I will tell you where we are right now, okay? Now, the problem is different in the sense. In the previous experiment, we want to have just one picture, okay? A good quality picture. The pyramid is not dynamic in the sense that, just one picture matters. In volcanology, you need to build a monitoring system, okay? Because you really need to know there are changes. A pyramid is a dynamic system. Now, is there a risk, okay? Well, in Mexico as a whole, there are over 200 known volcanic craters, okay? So Mexico is definitely a seismic, it's a volcanic country, okay? Now, there are active, as I said, there are like 12 volcanoes active, and the Popocatepetl is among the 3 most dangerous volcanoes worldwide, okay, for considering the size of the population that is at risk, okay? So there is another one called the Colima, in which there is less of a risk, but this population is closer, okay? We are going to be working on the Popocatepetl, which is the one you saw in the previous picture. The one, is this really a menace? Is there documented information that the Popocatepetl has done any harm to anyone? Okay, so this is what I'm going to elaborate now. The first question is are volcanoes in Mexico dangerous at all? I mean, why bother? No. So I will show you some examples of what these volcanoes have had as an effect. Some of you may have already born, few of you, I guess, when in Mexico the Paricutin erupted. Okay, Paricutin is a small, and I will just give you this idea. You see this shape here, which is not taken from the same side, but this shape is this shape. Okay, if you look it from an angle. And I don't know, there is sort of like a white thing here, which is this church here, okay? Now, you see here the beginnings of the volcano, okay? And this was taken in February of 1943, okay? And 2 months later, you have a mountain here, okay? So this is, and you have the church here, and now you see this thing, and the church is gone, okay? This is all covered with lava. So at least you can claim, okay, that these poor people, okay, did not like their city to be. So it is a menace to some population, this thing. And this is more, the Chichonal is a volcano that erupted in 1982, and it stopped the air traffic around Mexico for at least 1 week. It's a little bit similar to what happened in Iceland recently. And of course you have Mount Helen a little, sometime earlier on, that also was somehow a big disaster for air traffic and other things, okay? So in Mexico there are volcanoes, and volcanoes can threat. But this is, well, I would say something terrible, but only about 200 people die here, okay? So, because this is in a place where not much people live. But if this happens to the Colima, this is a recent photo of the Colima, then you're talking about different numbers, because there are about 300,000 people who live near the Colima, okay? And the Popocatepetl is this thing. If you ever been to Mexico, these are the 2 volcanoes that you have, and this is a lovely history, because this is a Popocatepetl, and this one has the shape of a woman, okay? And so this in Indian history, that Popocatepetl is this guy whose beloved lady was frozen, no? And so you see from Mexico City this thing. Okay, and Popocatepetl is po because it's an active volcano. It goes po from time to time. Okay, this is Mexico City and this is Puebla, and from here to there is about 40 kilometers either way. And Mexico City has, well, now over 20 million people. Okay, and you can see Mexico City and the volcano. There is no doubt that this thing represents a complication, okay? And this is the Popocatepetl view from the city of Puebla, okay? It's a smaller city, but still 3 million people. It's a lot. Is there a record of eruptions that could have affected? Well, there are numbers of well-documented eruptions, okay? But there were 2 major eruptions in the year 675 and the year 1095, okay, that produced massive ash slides. And, oops, I know I have to do this way, okay? And I just show you some examples. This is even earlier, 8,000 years ago, something that happened recently in a nearby town to Mexico City, near to the airport, to the Mexican International Airport, a place called Tocuila, okay? There was an interesting discovery. They found all these remains of mammoths, okay, that were all together. All the fossils were all together in one place. And they said, well, isn't that interesting? I mean, the mammoths were perhaps like elephants that would go die all in the same place or something. But they were too packed and too close together. And what they discovered is that the soil around are volcanic ashes, okay? And so the current explanation is that these guys were trapped, most likely in Pompeii, okay? Were trapped by a pyroclastic eruption by the Popocatepetl. So this is, I mean, if there were humans there, which have not been found, they'll probably run the same. Now, I don't know if you've ever been to Mexico, but the picture that I keep showing, this little mountain here is in fact a pyramid. It's the pyramid of I forgot the name. Anyway, but this pyramid was covered when the Spanish came to Mexico. They didn't know this was a pyramid, okay? And the pyramid was discovered later when they built this church on top, okay? And this pyramid was covered by a pyroclastic eruption of the Popocatepetl. So this civilization was also, I have to finish, okay, but I'm almost done, was almost wiped out by that, okay? Now, near in Mexico City, there are signs. This is a culture that was wiped out altogether. This is their pyramid, and all this was uncovered from the lava. So in Mexico City, we also have volcanoes. And if you have ever been to Mexico City, you will see that my university is all covered with, it's all built on top of lava. Now, what is the volcanological problem? Okay, is that you have a volcano. Volcanology is a pretty advanced science because it represents a menace. It's a pretty advanced science. It's very fine scientists working on this, but most of their information they obtain from the outside of the volcano. They go measure if this thing gets deformation, or they measure if there is seismic information and the amount of ashes and lava and so on. You record all that thing and build a model, okay? And the main part of the model is the size of the lava conduit, okay? That's part of your model, okay? But this thing, they don't know. They really don't know the dimensions of that thing. And that's something you can tell with muons, okay? So their model, they claim that using seismicity, which is now a well-known geological technique, you can more or less guess this thing to within about 100 meters, okay? The Japanese group that proposed this technique have come down to about 20 meters in the size, okay? So it's a better technique. And this, since I have no time, I just show you the detector put together by the Japanese in the, what is called, the Tsutsama Aoyama volcano, which is an island, that little thing. It's not a menace to anybody, no, it's not a populated, but this volcano produces as much sulfur as all the Japanese industry together. So this thing is a menace, that is an ecological menace, so it's kept, okay? And they are the first one to have ever used the technique and produced an image, and this is the image they produced. It was published in Nature 2 years ago, 1 year ago, okay? And they were able to locate this detector, this volcano erupted and was split in two, and they found already the original crater of that thing. Our project is very simple. It's similar to the other, except that it's much bigger. So we are out, instead of multi-wires, our wires are 20 microns thick. Now we are using PVC pipes to do our thing. And our detector is 10 meters square. We have no more money than that. We have been given that thing. This is the first prototype. We are already able to measure down to 10 centimeters the time. If a muon goes through this thing, you measure the time difference for the signal to go both ways, and you compare, you can get to about 500 picoseconds, the location where this thing, and 500 picoseconds is about 10 centimeters, okay? So somehow we have a good resolution in this along this coordinate. The pipe itself tells you the other coordinate, the location of the pipe. These are parallel pipes. The location both in the plane and arrow plane, because we are going to have 3 planes. So you have 3 coordinates and you can do that thing, okay? This is the results I was telling you about. This is time in nanoseconds, and this is the position, and this is basically what we measure is about 500 picoseconds. I'm not going to describe that as a function of another parameter. Does this has an impact? Okay. Well, I don't know if you follow Physics World, okay, but Physics World published in September a special issue on Mexican science, okay? And this, monitoring, smoking, great, explore, whatever, that's us, okay? So we already, I mean, this is important for science because Mexican politicians think that science, it doesn't have any good for Mexico, so this is important. These are my colleagues, especially this fellow here, who's an Armenian, who works for us. He was he was the former leader of the Yerevan group in Atlas, I believe, and now he lives in Mexico. And that's it. Thank you very much. And I'm sorry if I took 2 more minutes.
So now there's some time for questions or comments. Yes.
So for the volcanoes, where did you locate your detector? Is it deep underground? Or
This is only simulation. The detector is not yet there. We have a monitor. I showed a place where we are likely to place it. This is a collaboration with there. This is a collaboration with, of course, volcanologists, okay? And so there is a place, this is not shown in here, there is a place that has a little flat part where we think we are going to place our detector. What is limiting, and I didn't discuss, is that you cannot go very far down in this conic thing because of the limit of the 10 kilometers, okay? If this thing is more than 5 kilometers, this 10 kilometers equivalent of water for soil is about 5 kilometers, okay? Density 2. So somehow we cannot go further down than that, okay? It's not yet installed, and well, we first have to build the detector. Yes?
Well, my question is a random archaeology one. When you were talking about the pyramid of the sun, tunnel, you said that was human-made, right? The tunnel?
The archaeologists tell us that was human built.
It's very tall.
Hmm?
I was surprised that it was so tall. It was comfortable. for 20th century, 21st century?
Well, I mean, I'll show you my friends. I know my friends. I think they are all right next to in this photo. My friends are in that tunnel. The ones it's tall at places, but in places you have to walk like this. Yes, yes. Yes. I mean, this is a good comment, but it's not comfortable all the time. Okay, you have to work your way. Yes.
So can you put your muon source from the side of your volcano or pyramid and put detector on the other side, so you can just do this, horizontal kind of image?
Yeah, in principle it can be done. Yes, but if you ask one of my high energy physicist friends to produce a muon source accelerator, a muon accelerator, okay, that would be pretty expensive, okay? And I don't know if you can. Well, of course you cannot do that in a pyramid, okay? Because they would not. I mean, they did not allow us to touch the the anything, no. So no, you cannot. I mean, in this sense, that's not an alternative. I've never seen. I mean, we are not the first ones to use this technique. There are people with resources. I mean, you may say, well, because you're Mexicans, but the Japanese have a lot more money. But there are people with resources that have not relied on producing a source. Okay, they use the natural source. What you are proposing would make any of this imaging much faster. That would be what you would gain. Okay, but it has not been judged necessary. Okay. Yes, sir.
I got the impression you're saying you're hoping to measure the nature of the magma conduit. Is magma a different density than the surrounding rock?
No, no. The lava tunnel, okay, the lava conduit is empty. This is where the fumes come out. Okay, so if it is filled, then the volcano will open another conduit. Okay, there is always, because this thing is like a pot. Okay, you have pressure, and this thing is kept empty. So it's through that hole, through that tunnel, that the lava will flow. Okay, and it's usually kept empty by the pressure of the gases. Okay. Yes.
Judy's question made me think: what is the angular range that you're able to cover?
Yes.
You can't follow from the side because the atmosphere is too thick and you don't have flux.
No, that's not the case. I mean, when we started this thing, I knew nothing about astroparticle physics, and I just followed Luis Alvarez's idea of doing these transmission measurements from inside the pyramid, because there was already a tunnel, but you can measure from the outside too. The distribution, if you are in space, okay, in space, you could measure a uniform. Your primary cosmic rays will come to you uniformly from everywhere if you were in space. Now, it's true that if your muons are produced, I mean, are secondary radiation that is produced in top of the atmosphere, your count will depend on angle, okay? Yeah. Because you have more mass, more atmosphere to cross this way than this way,
yeah,
okay?
That's my question. How big is that angle?
The point is that the effect that happens in the spectra, I didn't. The answer to your question is in one picture here. So if I am allowed to show this thing quickly, your question is an excellent question and allows me to show you this. Okay, this is at 0 degrees. Okay, and this is at I don't have it here, but I think this is about 20 degrees inclination. And what happens is that you lose your low energy muons, your spectra hardens, okay? But still, the count rate at the maximum, is about the same, okay? It's about the same. And what happens in the volcano, which is is that in the volcano, you are going to be chopping up most of your yield because it stops, it attenuates. It's only the highest energy yield, and that is, let's say that you have to take that into account in the simulation, but there is no problem. There's no problem.
Okay, so I don't see any other comments, so thanks again.
Okay, well, thank you.